Hello everyone. In this video we are going to discuss about elementary signals. Elementary signals are nothing but basic signals that occur frequently whenever we think of the signals, the very basic signals that comes to our problematic subjects or in our day-to-day life in the nature that occur are called as elementary signals. These signals are used to build the next level complex signals. Okay, any physical signal that can be modeled, whatever may be the signal physicality, we can model such physical signals using these elementary signals. Okay, while discussing the elementary signals, we have the classifications of them. First one is elementary continuous time signals, and the second one is elementary discrete time signals. Okay, in this video we are going to discuss about elementary continuous time signals. Okay, specifically we are going to discuss about elementary continuous time signals. Okay, in elementary continuous time signals we have subclassifications. Elementary continuous time signals, in elementary continuous time signal we have subclassifications. Among them, first one is unit step function, okay. Second one is unit impulse function. Third one is unit ramp function. Fourth one, exponential signals. Fifth one is sinusoidal signals. Sixth one is exponentially damped sinusoidal signals. Okay, these are the six subclassifications when we comes to elementary continuous time signal. Okay, I'll repeat once again: unit step function, unit impulse function, unit ramp function, exponential signal, sinusoidal signal, and exponentially damped sinusoidal signal. Okay, let us study all these six elementary continuous time signals in detail. Okay, first one is unit step functions. Unit step function is denoted by symbol u of t. U of t. Since it is a continuous time, we are dealing with elementary continuous time signals, we are marking it as t. Unit u continuous time t. Unit step function is represented by u of t. Okay, this continuous time unit step function is defined as, this unit step function u of t is defined as the value of u of t is equal to 1 the value of u of t is equal to 1. Since it is unit step, unit means 1, u of t is equal to 1 for time t is greater than or equal to 0, and the u of t value is 0 for t less than 0. Hope you people can understand. The value of u of t is 1 unit step function. Unit itself says 1, so u of t value is 1 for t greater than or equal to 0, and its value is 0 for t less than 0. If you want to represent it graphically, t the value of u of t is 1 for t greater than or equal to 0. For every value of t greater than or equal to 0, the u of t value is 1. It's a constant line. Okay, it's a flat line starting at t is equal to 0 till infinity. Since it is greater than or equal to 0, it is not telling where to stop. Okay, t is less than, there is no t is less than value, so it moves till infinity. It keeps on going till infinity. Okay, the u of t value is 1 for t greater than or equal to 0, and u of t value is 0 for t less than 0. For t less than 0, u of t value is 0. Okay, and hope you people can link with me. The second one is the second function is elementary continuous time signal is unit impulse. Unit impulse function. The second one is unit impulse function, which is represented by delta of t. Since it is a continuous time, we are talking about elementary continuous time signal. All signals are represented by t. Unit impulse function is represented by delta of t. Okay. The continuous time unit impulse function is defined as delta of t is equal to 1 unit impulse. Okay, since it is unit impulse, delta of t is equal to 1 unit for 1 impulse at t is equal to 0. The value of delta t is equal to 1 only at t is equal to 0, and delta of t is equal to 0 for t not equal to 0. Value of delta of t is equal to 1 for t is equal to 0, and delta of t is equal to 0 for t not equal to 0. And if you want to represent it graphically, t at t is equal to 0, the value is 1. For t not equal to 0, it is 0. Positive values of t is also 0, and for negative values of t, delta of t is 0. Okay, this is a unit impulse function. Unit impulse, delta of t is equal to 1 only at t is equal to 0, whereas u of t is equal to 1 for t greater than or equal to 0. After 0, it keeps on going. That's a flat line unit. Okay, and the third one is unit ramp function. Third function is unit ramp function, and it is denoted by r of t. Since it is a ramp, r of t. Okay, we are dealing with unit ramp function r of t. Okay, for a ramp function, since it is unit ramp, the slope of the unit ramp function is always unity. Okay, the slope of the unit ramp function is always unity. Graphical representation of a unit ramp function can be done like 0. As I said, the slope of the unit ramp function should be unity, which means at a t is equal to 1, the amplitude will be 1. Okay, it's a unit ramp function, it keeps on increasing. At a t is equal to 1, the amplitude is 1, and at t is equal to 2, the amplitude will be 2. Okay, amplitude will be 2 at t is equal to 2. This will be the unit ramp function. Since I am not using any scales, the graph is slightly curved. Okay, hope you people understand. The slope should be, wherever you measure, the slope should be equal to 1, which means the slope of the unit ramp function is always unity. Okay, next function is exponential continuous signals. Exponential continuous signals. Exponential continuous time signals are represented by x of t is equal to e power at. Exponential term, x of t is equal to e power at. Okay, and these exponential signals are of two types. One is growing exponential functions, and another one is decaying exponential functions. X of t is equal to e power at is a growing exponential function. You can see it is growing, exponentially growing. X of t is equal to e power at is a growing exponential function for a greater than 0. For a value greater than 0, which means 1, 2, 3, e power 1, e power 2, e power 3. If it is positive values, if the value of a is positive, x of t is exponentially growing. And if x of t is equal to e power at is a decaying exponential function for a less than 0, which means the value of a is negative. For negative values of a, x of t is equal to e power at is a decaying exponential function. For positive values of a, x of t is equal to e power at is a growing exponential function. Okay, this is about exponential signals. And next one is sinusoidal signal. The next function is fifth one, sinusoidal signals. Next function is sinusoidal signal. A continuous time sinusoidal signal is given by x of t is equal to a cos omega naught t plus phi. Continuous time sinusoidal signal is given by x of t is equal to a cos omega naught t plus phi, where omega naught is equal to 2 pi f. We call it as angular frequency, which is in terms of radian per second, and phi is phase shift. Value of phi is phase shift, and f is linear frequency. F is linear frequency. Okay, and the sinusoidal signal, if you want to represent it graphically, you can represent it in a sine wave format. T0, x of t is equal to a cos omega naught to t plus 5. For t is equal to 0, omega naught into t is 0. For phi is equal to 0, cos 0 is okay, like that we can manipulate. Or omega naught at a t is equal to 0, phi is 90 degree, we can take phi as 90, cos 90 is 0. Okay, it becomes a sine wave. Okay. At t is equal to 0, if phi is 90, we will get this waveform, and at t is equal to 0, phi is equal to 0, we will be getting a cos waveform. Okay, this is about sinusoidal signal. And the last function is exponentially damped sinusoidal signal. Exponentially damped sinusoidal signal. These exponentially damped sinusoidal signals are given by x of t is equal to e power minus at sine omega t, where a is greater than 0. Since we are already considering it as minus a should be positive value, so that it becomes e power minus, if a is positive, if a is equal to plus 1, it would be minus of plus 1 is minus 1t, like that. Okay, since it is e power minus at, it is exponentially damping signal. Okay, which means decaying signal, e power at. If a is less than 1 or less than 0, which means negative values of a, it is a decaying exponential signal. Okay. If we multiply a decaying exponential signal with a sine wave, we will be getting an exponentially damped sinusoidal signal. Okay, this is x of t is equal to e power minus at into sine omega t. This is called as an exponentially damped signal. This is about elementary continuous time signals. In the next video, we will be discussing elementary discrete time signals. If you people have any doubts, please do message on my comment box. We'll be connected. Thank you.